All right. Coming up next, we have Dr. Saad. He's a senior manager application engineer for autonomous solutions with Ansys. And he's going to be talking to us today about a solution study in machine learning and physics-based radar simulation in autonomous vehicles. Hi, Dr. Mate, and the floor is yours.
Thank you very much. I trust you can see me and you can hear me.
Yeah, we can.
Perfect. So just give me a second to show my screen. There you go. Okay, can you see my screen?
Brilliant. Yeah, hear you loud and clear and see your screen. Excellent. Thank you.
Perfect. Thank you. So thanks for the introduction. And today I will be talking about machine learning and physics-based radar simulation in autonomous vehicles. My name is Saad. I'm actually leading the autonomous simulation team in EMEA at Ansys. For today, I will be giving a short introduction. I think already most probably everyone already know about what's AI, why do we need it and whatnot, but it's good just to set the floor a little bit. I will promise, relatively fast through that. And then I will be talking about Ansys physics-based radar simulation as an enabler for machine learning-based applications in electromagnetic domain, so to say. And then give a short approach on the simulation toolchain we have used for providing these or for enabling these applications. And finally, I will give a little bit of an overview of some of these proof of concepts that we have done and some experimental or preliminary results. So starting with the introduction, the problem in AI, and several people will actually add to this or even complement or in some cases also disagree for this, but it remains more or less a critical fact or a very obvious fact that like data collection, managing the data, cleaning the data, taking care of privacy issues, for example, or even having it available on demand for you is definitely a problem. And actually, going toward or trying to mitigate some of these problems and going toward synthetic data will actually solve the problem. Whether that's entirely going from real data to synthetic data or simulation data or hybrid transitions or semi-transitions, it doesn't really matter. The idea is actually synthetic data have been actually proven to be functional and to be useful for training AI or for testing AI or for even enhancing its capabilities. For machine learning, as you already know, it needs really a lot of high quality data to work well. So it's not only about the quantity of the data, right? For autonomous vehicles or for testing or virtual verification of autonomous vehicles, we talk about a big number of mileage to be driven, to assume or to ensure, let's say, to ensure safety, more or less. However, we also talk about the relevance of this mileage to be driven. It's the same more or less on machine learning. However, there you still need this huge amount of data, and you still need to know that this data actually is annotated well, is actually labeled correctly, and actually reflects the situations that would make sense for your machine learning algorithms, that will ensure your machine learning algorithms are actually not overfitting, are capable to generalize, and so on. So what we saw, and this is some study I just pulled out, just to give you an idea from what's the general feel behind that. So we see in computer vision, for example, I know I will be talking about radar, but I'm making the analogy for computer vision just to actually highlight the fact that the lack of data in radar or for electromagnetic applications, automotive radar applications, is definitely an issue over here. So from 300 computer vision professionals just trying to use AI and machine learning, 50% are actually already using publicly available synthetic data. And 38% of those, so 38% of the other 50% actually is planning on using synthetic data also by the end of 2022. Here, I want to point out two main issues or two main key points, which is first, publicly available data set. So basically, you don't really have that much of a leverage of what's available publicly. You just use what's available for you. And definitely the fidelity or the quality of this data may vary, right? The quality of the data from a perspective of acquiring it and from the perspective of actually labeling it as well. And adding to that, we also see 57% of these professionals, let's say, reported that the lack of edge cases that can be covered in this publicly available data set, right, have actually slowed down the training process and, let's say, the next step of achieving the target that may be average precision or whatever the neural network is meant to do in this case. To tackle this effort, like or to increase or to actually point out also what's happening at a scale from different consortium and not only Ansys or not only one or two OEMs, we see AI SEE, that's a European funded project, which here it's aiming to see, okay, how good our AI is actually traveling or in supporting applications and autonomous driving situations or scenarios in adverse weather conditions like bad weather conditions, fog, rain, snow, as well as different light conditions, so daytime or actually nighttime or dawn or dusk, where you have some edge cases which correspond probably to the position of the sun or whatnot. So this is not only focusing on camera, of course, this is focusing on camera, radar, and LiDAR in general. And you see the list of consortium. There's a link also over there. You can go in and take more information about that. The key point is that it's something that's being addressed from an OEM perspective, from a Tier 1 perspective, from software provider perspective, from universities, and so on, right? In addition to that, another, and these are all current ongoing projects where Ansys is actually a partner in them. Another ongoing application or another ongoing project, that's a German funded project, that's actually developing methods and tools that will generate the preparation of training and validation to safeguard data for AI functions in autonomous vehicles. And here again, we see a huge number of universities, technology providers, tier ones, OEMs, and so on, also contributing to these projects, right? Again, this is just to highlight the fact that having this capabilities or extending and collaborating more or less from a different aspects across the industry will only brings us closer to understanding the needs, the current problems, and how we can eventually leverage synthetic data for these approaches, definitely in AI. In a radar perspective, when it comes to radar, there are several AI-based applications. So I can't like anything that you can think of, a computer vision algorithm is actually able to perform based on AI or machine learning or neural networks or deep neural networks. You can also sort of transfer it toward radar applications, right? Currently, you measure data, you do the data labeling, and then you train your ML. The goal here is actually to go from simulated radar data, and intentionally, I'm not putting data labeling, not because the data is not labeled anymore, however, because the effort for labeling this data is almost none, simply because of the fact that you have access to the entire ground truth, right? You are entitled, or you know exactly where your positions are, where your objects are at each and every simulation frame. So how we are basing our simulations, like we don't only want to generate accurate and, let's say, labeled data automatically. However, we also want to generate it at a very fast rate, right? Our main electromagnetic solver, let's say, that's actually being used for electromagnetic simulation is HFSS based on SPR+. That's more or less the golden standard in the industry for electromagnetic simulations in general, right? So based on this technology that is already validated by numerous customer testimonies, numerous, let's say, publications, and actually correlation studies. We took that and we brought in HFSS, or we brought in real-time radar, which is benefiting from the fact that, or using in general, like the hardware acceleration, so GPUs, to accelerate this entire process, going from solving some, I don't know, 1 frame per 30 minutes, maybe, to solving 30 frames per second, so to say. And it's not that we only took this correlation study, or we proven like the fidelity or the quality of our simulation just by basing it or double checking it with what we previously have as an HFSS SBR+, but we also went and just used this new technology and modeled a industry available automotive radar, that's the SRR 520 from Continental, and did some correlation studies. Now, these correlation studies have till now shown a 0.19% deviation, almost close to nothing, when comparing range returns. So in this scenario, we actually replicated a real scenario inside our virtual world and then actually tested that. How does this all work? As I previously said, we had at the very beginning what we called HFSS SBR+. Throughout some algorithmic accelerations or optimizations, 1,000 times factor have been improved, have been achieved to solve this specific frame. A typical scenario. It's not like just a corner reflector or whatnot. No, it's really a typical complex scenario encountered in real life. And from 2022, what we took is actually we boosted this technology and we transferred this technology to run on hardware accelerated devices like these GPUs that we're talking about, and achieved in that a 10 to 20 millisecond simulation time for solving this 1 frame. With that, of course, we are definitely talking about, or always in my presentation now, I'm talking about physics-based simulation, not just simulation. So adding these features, like in the ability to introduce parametric antenna for fast and rapid prototyping, or even far field data, meaning the effect of the bumper, for example, or the paint, or the radome, or the cover of the radar on the final beam or antenna patterns, right, can actually be directly integrated and then directly used inside the simulation, which brings the fidelity of the simulation up to a next level. And the possibility to implement or to just run different waveforms like pulse Doppler or FMCW, commonly used in the industry, on the automotive industry, are also 2 main options over here. We can talk about radar simulation without talking about multi-bounds, right? So it's a very distinctive feature of radars, being to be able to see beyond the line of sight. So here we can see a single bounce and the effect of it on a range Doppler map over here. You see some returns, which is good. 2 bounces are definitely better, 3 bounces even better, and 4 bounces even more accurate and more close to what you actually see inside your simulation. So that's definitely a very essential feature if you want to say, I'm as close as possible to what a real radar will actually see inside the simulation. Of course, physics-based simulation comes also hand in hand with material and the electric material properties for radar applications. So all of these are included, as well as must-have features, right? Where different layers, different coating layers can actually be implemented and assigned to different mesh components inside your geometry. So here you see just an example with the intersection. If everything is metallic, and if you go and say, well, my road have the electric material properties for asphalt, and well, you can see the difference in the output, in the scattered or in the reflected energies in this range Doppler map. Surface roughness, again, that's also very important, considering the fact that you don't only want to see specular reflections, and now with this new trend of 4D radars, 4D imaging radars, so radars that can actually also see in azimuth, so horizontal field of view more or less, and elevation, vertical field of view. I'm just making the analogy with cameras more or less. you need to see this azimuth spread and this elevation spread so that you can actually eventually also create your 3D point cloud. Yes, 3D point cloud, not from a LiDAR, but from a radar, right? From a 4D radar. These are complex radars with high number of antennas. So surface roughness is also here a must-have to be as close as possible to what you will obtain from real simulations. This is just an example also on flat road on the left side, where you can see really the reflections like not that much, and rough road where you can see really the contribution of the surface roughness into the range Doppler map. And just FYI, in the end, the range Doppler map is or the data that's being produced from this range Doppler map is then later on being used to do some more post-processing, create object lists, point clouds, and whatnot. Microdoppler effect, that's a distinctive, let's say, more or less final property that's a must as well for radar simulations. These are unique signatures of bodies or objects inside your simulation or inside your real world that have associated angular velocities to them, so that they are moving in some circular pattern, right? So if you see this plate, for example, moving, if you just consider the linear motion of it, you would see the signature of it on the range Doppler or something like this. If you actually go and include also the rotations, you can definitely see a very distinctive range Doppler signature over here that distinguishes an object that's having only a linear velocity and an object that's having some angular velocity. So if I just make the analogy to what does this mean in the real world, you can think about a cyclist, right? So a cyclist that's actually pedaling, or a rotating wheel, or actually a moving hands and moving legs of a pedestrian. These will all produce unique signatures, which will later on help machine learning algorithms to classify or identify these objects as probably non-vehicles or pedestrians or cyclists and so on. And finally, because we know there is a big trend in simulating multiple radars to reach a better, let's say, some level of autonomy, so to say. And also, even if you just want to simulate one imaging radar, can range up to 24 by 24 antennas or 48 by 48 antennas. So that's almost a total of 2,300 something channels, right? No one GPU can handle all of this data on its own, simply because you don't have enough memory on one GPU. And here comes the magic of auto configuration, which will automatically configure your batches, configure your channels, configure all of the parameters that you have as an input for this auto config, so to say, and then will optimize or will solve a minimization problem to give you the best configuration so that it's actually running all of this. It's being able to fit this entire environment or this entire problem at each frame into a number of batches on the available GPUs that you have on your machine. So how do we interact with this tool? This is also, again, a very distinctive feature of it, simply because here we are not talking about a graphical user interface. We understand the need to actually distribute the simulation to be able to script it, batch it, and just run thousands or hundreds of simulations like automatically. So the entire interaction with this tool can be done with an API, so a well-documented, available to use open API that anyone can just interact with it. And basically you just, let's say, parameterize your sensor, make sure that your material properties are assigned to your 3D geometry, feed it through an API again, and then add the dynamic behavior. So communicate with this simulation tool or with this sensor simulation tool, communicate with it the actual position, the actual orientation and velocities of each and every model in your system or entity in your system, and finally obtain your sensor output auxiliary data, which is probably what you will need for labeled data more or less, and feedback control data that enables you also to do some optimization during some runtime, some configuration. In the case of a radar, it's basically the raw IQ data that you can get, so post ADC directly, and processed range Doppler data. Also, it's like if either one of those is okay, depending on the use case. We definitely also went and have this directly implemented in some available driving simulators like CarMaker over here. You can see on the left side the output of the radar, and here on the right side, output of a LiDAR. The camera can also be as an output for physics-based simulation. Not only because it's an open API, we also did this integrations with Carla. That's an open source available tool. I don't know how to hide this one. Doesn't matter. And we also went and show, okay, what can we do without, okay, this is getting a bit annoying, but okay, what can we do also with this open API, right? Without actually using any driving simulator. So this is just a scripted simulation, right? So here we are not using any driving simulator. This is just really a script that we wrote to indicate what can be done also if you just have some data running around or fleet data from your measurements on the road and so on. Okay, so how does a simulation toolchain for machine learning look like? You know, you have data generation, you have neural network, and you have neural network evaluation. So to test the neural network, what we concentrate in at Ansys, that's our core capabilities, is actually the variation data set and how to generate the scenarios, run them, and obtain label data. And here on the right side, you can see this output is then provided to a neural network. And later on, some evaluation is being done directly on the neural network, which we consider these two aspects as black box containers, right? As long as our output is well documented, is well labeled, and reflects what, let's say, what the sensor configuration is being used here on the left side, we just can provide this data as a standard, let's say, output, and then the user or the consumer of this data can actually do or use it for their own application. Okay, I said I will provide also some information of what we have done for this aspects, or some experimental results and some proof of concept. So first of all, we went and we said, okay, let's use this for object detection based on range Doppler maps. So what we have done is we have built this this tool chain that just goes through the scenario variation, and based on a predefined set of parameters, it can automatically generate like a big amount of sensors or a big amount of scenarios that will be fed to this driving simulator and the sensor simulator, and then provide you with the output as labeled data. So in this regard, what we obtained labeled range Doppler data, right? And each radar signature was indicating, well, is this a car, is this a motorcycle, or is this a bus? This was directly fed into the data preparation and the neural network. So this data that you see here on the left side. And the neural network just did this job for training. And then we got our preliminary results, so to say. Again, this is the ego vehicle driving, and this is the output of the neural network, right? Again, we are not really in the business of training neural networks, but we are in the business more or less of doing physics-based simulation and show how they can be used for these applications, right? So keep in mind, we didn't go and undertake any, let's say, any neural network optimization, parameter tunings, and whatnot, but we just went and tried to train something and to show that it actually works. We took this a little bit further, and here we said, okay, you know, there's also reinforcement learning, so more or less unsupervised learning. And what we have done over here is we went through a series of webinars. You can find that also on the Carla website or on our website to see how we have trained this network just to actually break based on range Doppler data without any post-processing to control the longitudinal to execute or to perform a longitudinal control of the vehicle. More interestingly, and this is something that I really like the study because we directly correlated the output or tested the output of this neural network on real data. What we have done is actually we took spectrograms. So spectrograms have a very good record at being used for training neural networks for identifying activities. That's from the literature, so to say. And what we have done is actually we trained these networks. So we generated these spectrograms at the beginning, and we tried to identify if the object or if the pedestrian in front of us is falling, is standing idle, or is actually walking. So our colleague bought radar and just measured the data, went and did open field measurements with the data while he's falling, while he's standing, and while he's actually walking. And then we did the same in simulation, right? So on the left side, you can see the output of the measured data from this radar. Information about this radar can also be provided. And on the right side, you can see the output of the simulation, walking, standing, and this is just an example, one falling, right? So in the end, we had a huge amount of data, similarly using the previous tool chain that we have showed on walking, standing, and falling. And we just dumped this data to disk and used this data as the same tool chain to train the neural network only on virtual data. So the neural network here just saw virtual data, did not see any measured data. The measured data that I'm showing over here was actually later on used just for testing. And what we observed is, if you take a look at this confusion matrix, the predicted labels here on the x-axis, and you see falling, standing, or walking. And if you take a look on the left side, so on the y-axis, where you see the truth labels, when it's walking, standing, and falling, this was the only task of this classification algorithm, just to say, okay, is my pedestrian walking, falling, or standing idle? And we saw an 86% classification accuracy on measured data. Again, the network have only seen simulated data and have been tested only on measured data, which for us is really a good and a very clear statement of the feasibility of this approach, at least for this application, right? Again, no hyper tuning, no optimization, no transfer learning, nothing have been done in this regard, just simple, straightforward approaches. In conclusion, my main takeaway is actually we go from the real world to the virtual world, and we try to bridge the gaps between these two worlds, not only with simulations, but actually with physics-based simulation, so that it will eventually be relevant and applicable when training and when executing your, let's say, your development on the virtual world and trying to go to the real world and see, well, will it make sense? Will it really help or not? That was from my side. These are my contact information. If you want to reach out, or if you have any questions, or you want to dig more deeper into any of my results.
Thank you, Dr. Kmeit. I think we're out of time, but we have time for one quick question from the panel. The question is, can you tell us more about your recent announcement regarding your work with BMW Group, co-developing simulation software for autonomous vehicles?
Okay, so aside from what's being announced, I can't really reveal, but we can definitely take that offline if that's necessary.
Offline.
So yeah, exactly.
That's brilliant. Okay. Fair enough. Thank you very much for your time, Dr. Kmeit. And yeah.
Thank you. My pleasure.